Hello everyone. In this video, I'm gonna give an introduction to eigenvalues and eigenvectors of a square matrix. So first, we're gonna start off with the geometric interpretation of eigenvalues and eigenvectors. Then we will see the official definition. After that, we will try to figure out how to find eigenvalues and eigenvectors of a general n by n matrix. All right. We know that when we multiply a vector by a matrix, basically we are gonna get a linear transformation of that vector, right? So here, consider matrix A, it's a 2 by 2 matrix, and vector V. So this is vector V, right? And if I multiply A by V, what I get here is the vector 6 and 7, right? So this is actually the linear transformation of vector V by matrix A. So if I draw that, let me first show the line in which vector V is. Now, this is gonna be vector AV, right? So this is AV, and this is vector V. Okay, so what happens is that most of the time when you multiply a vector by a matrix, the image or the linear transformation is gonna get knocked off the line on which the original vector was on. Okay, so the result is not gonna be, usually it's not gonna be collinear to vector V. All right, let's try this vector, vector 1, 1. So this is vector 1, 1. So this is vector V, and this is the line that vector V is on. And if we multiply matrix A by V, we are gonna get the vector 5 and 5. Okay, so if I draw this on the plane, it's gonna be this vector. So as you see, a V is exactly on the same line as vector V. So in other words, they are collinear. Okay, as I said, most of the time this is not going to happen, but if this happens, if they're collinear, then vector V is a special vector for matrix A. Okay, so as you see, vector AV is going to be a scalar multiple of vector V, right? In fact, in this example, vector AV is equal to 5 times vector V, right? 5 times 1, 1 gives you 5, 5, okay? And these are the vectors that we are going to focus on in this video. And these are called eigenvectors corresponding to matrix A. All right, let's see the official definition. So let A to be an n by n matrix, a square matrix, and let V be a non-zero vector of size n. So a non-zero n by 1 vector. Okay. So here, if for some scalar, let's call it lambda, so for some scalar lambda, if A times V is a scalar multiple of V, lambda V, then the scalar lambda is a special scalar called eigenvalue. So this is an eigenvalue of matrix A, and vector V is called an eigenvector corresponding to lambda. So V is an eigenvector of matrix A corresponding to eigenvalue lambda. All right, now we know what is the definition. Let's figure out how to find eigenvalues and eigenvectors of an n by n matrix. All right, I'm going to start with finding eigenvalues. So finding eigenvalues of matrix A here. I'm going to start off with this equation, okay, with the definition. So I know that AV is equal to lambda V if V is an eigenvector and lambda the corresponding eigenvalue, right? Here I don't know what is the value of lambda and V. I just know their relation, right? Now, in the right hand side, this is a vector which I can replace it with lambda times identity matrix of the same size as V times V, right? So identity times any vector or matrix give the same vector or matrix. So I'm not changing anything. And I'm going to just rewrite the left-hand side. So here I have two vectors of the same size, of size n by 1, and they are equal. It means that their difference must be the zero vector. So AV minus lambda identity times V gives me the zero vector of size n. All right, now here in these two terms, I can factor out V, right? So I can rewrite the left-hand side as A minus lambda times identity times vector V is equal to vector 0. All right, so if I focus on this equation, I can see that this is actually a matrix times a vector equal to 0, which is a homogeneous linear system, right? And we know that how to solve these kinds of systems. But the condition we have on V is that we want V to be non-zero based on the definition, right? We want V to be non-zero. So for this homogeneous linear system, I want the solution to be non-trivial, right? Non-zero. So by the equivalence theorem of linear algebra, or actually invertible matrix theorem, I know that this homogeneous system has a non-trivial solution if and only if this matrix in the system is non-invertible, or in other words, the determinant is equal to 0. So I want the determinant of this matrix to be 0. So we want the determinant of A minus lambda times identity to be equal to 0. Again, here, we know that lambda is a variable here, right? We haven't found it yet. So this term, if I expand this gives me a polynomial of degree n in terms of lambda. So this is a polynomial of degree n, and actually it has a special name. So let me call this polynomial by p of lambda. And this is actually called the characteristic polynomial for my matrix A, okay? And if I consider the whole equation, so the characteristic polynomial equal to 0, this equation, the whole thing here, this equation is called the characteristic equation. So this is characteristic equation. All right, so again, the goal is to find lambda and eventually find v. So if this polynomial is equal to 0, it means that the solution will give me the eigenvalues, the lambdas, right? So basically, the eigenvalues of a matrix are actually roots of its characteristic polynomial. So the roots of the characteristic polynomial are basically eigenvalues of matrix A. All right, now we know how to find eigenvalues. Let's see it on our example. All right, so let's form the characteristic polynomial of this matrix. So the characteristic polynomial here, P of lambda, is equal to the determinant of A minus lambda times identity of size 2, right? Because here my matrix is of size 2, so the identity matrix is of size 2. And this is gonna be the determinant of A minus lambda 0, 0, lambda, which is gonna be the determinant of the matrix 1 minus lambda, 4, 2, 3 minus lambda. And we know how to find the determinant of 2 by 2 matrices easily, right? So I'm gonna multiply the terms on the diagonal minus the product of the terms on the off diagonal. Okay, and if I simplify this or expand this, I'll get 3 minus lambda minus 3 lambda plus lambda squared minus 4. And if I simplify and reorder this, I'll get lambda squared minus 4 lambda, sorry, this is 8, minus 5, right? So here I have a quadratic polynomial, right? This is a quadratic polynomial, and I know how to find the roots of this quadratic polynomial. Either I can use quadratic equations, or I look for two numbers for which their addition is -4 and their multiplication is -5. And I can write this as lambda. So those two numbers are -4, -5, and +1. So lambda minus 5, lambda plus 1. And I know that the roots of this polynomial gives me the eigenvalues. So if I set this to be 0, either this term is 0 or this term is 0. So setting this to be 0 gives me 5. Setting this one to be 0 giving me -1. And these are the two eigenvalues of this matrix. We already saw this in the example at the beginning, right? So eigenvalues of A are lambda 1 being 5, lambda 2 being -1. All right. Now that we have the eigenvalues, the question is, how can we find eigenvectors? So here, let's look at this equation again, okay? If I know what is lambda, so if I know the lambdas here, and if I substitute it here, I will get a homogeneous system, and the solution, then the trivial solution gives me the eigenvalues, right? So let's try that. All right, so as I said, we already know that A minus lambda times identity times V must be equal to 0 vector. Now, I'm gonna first start off with lambda 1. So for lambda 1, I'm gonna replace lambda here with 5, okay? So we get A minus 5 identity times vector v is equal to 0. And here in this example, matrix A is of size 2, so this is identity of size 2, vector v is of size 2, 0 is a 0 vector of size 2. So I'm going to just expand this. So I have A minus 5 times identity times vector v, which I'm going to write it as v1, v2, to be equal to 0, 0. So in other words, I have negative 4, 4, 2, negative 2 times v1, v2 equal to 0 and 0. So this is a homogeneous system with two equations and two unknowns. There are many simple methods to solve this linear system, right? You can just use one equation to eliminate one of the variables, substitute the other equation, and simply find the solution, right? But what if I have a bigger matrix? What if I have a 3 by 3, 4 by 4 matrix? What can I do? So I'm going to use the general method of solving a linear system, which is Gaussian elimination here, just for the sake of practice. So using Gaussian elimination, I'm going to form the augmented matrix, which is negative 4, 4, 0, 2, negative 2, 0, right? And I'm going to try to use row operations to form the row echelon form, right? So pick the first non-zero entry of the first row, scale this. So row 1 being scaled by negative 1 over 4. And I'll get 1, negative 1, 0, 2, negative 2, 0. And I'm going to use this to make whatever under it to be 0. So I'm going to use replacement. So replace row 2 with row 2 minus 2 times row 1, and I'll get 1, negative 1, 0, 0, 0, 0. And this is the row echelon form, right? And I know that this corresponds to V1, this corresponds to V2, this is equation 1, equation 2. So this is a leading entry, so V1 is going to be a leading variable, and V2 is going to be a free variable, right? So set V2 to be a parameter t, for t being in R, and use equation 1 to find V1. So V1, 1 times V1 minus V2 is 0. I can replace V2 with t, so I'll get V1 minus t equal to 0, which gives me V1 equal to t. So the solution for this one is gonna be V equal to t and t, or I can factor out t. I get t times 1 and 1, for t being a real number. So this is actually giving me the set of eigenvectors corresponding to eigenvalue 5. So for different t's, you will get different vectors, right? And all of them are actually eigenvectors of lambda 1 being 5. In particular, if t is 1, then this gives you one example of eigenvectors of 5, eigenvalue of 5, and this is exactly the vector we saw at the beginning in the example, in the geometric interpretation, right? So all eigenvectors are going to be a scalar multiple of this vector. So these are eigenvectors of matrix A corresponding to eigenvalue 5. All right, so we can repeat this step for the other eigenvalue to find the set of eigenvectors corresponding to that eigenvalue. So for lambda 2 being negative 1. Again, I'm gonna use this equation and I'm gonna find eigenvectors corresponding to this. So here, if I replace lambda with negative 1, I get a minus identity, which is going to be plus identity, times v is 0. So this is basically matrix A plus identity times v being 0. So if I add them, I'll get 2, 4, 2, 4, 0. 2, 4, 2, 4 times v1, v2 being equal to 0 and 0. And again, form the augmented matrix, right? So you will get, so the augmented matrix which is gonna be 2, 4, 2, 4, 0, 0. And if you actually form the row echelon form, I'm gonna skip this part. I'll leave it as an exercise to you. I know that you know how to use Gaussian elimination. So if you form the REF, you will get 1, 2, 0, 0, 0, and 0. Okay, and this gives me the set of solution negative 2t and t, which I can factor out t, negative 2 and 1 for t being in R, and these are eigenvectors corresponding to lambda being negative 1.